Okay, so example 3. All right, now let's go ahead and let f of x, y, z, we'll do a function of 3 variables, x squared, y, z cubed. So you see that you plug in a vector, a 3 vector, and it spits out a number. It's a mapping from R3 to R. Well, let's see. Let's go ahead and let C of t, the curve along which we parameterize, let it be the spiral in 3 space defined by cosine t, sine t, and t. And let's go ahead and let t go from 0 to 3 pi over 4. So just to let you know what this looks like, I'm going to draw out my 3-dimensional. Okay, and I'll go ahead and go back that way, this way. So this thing that's coming out is the x-axis, this thing is the y-axis, and this is the z. So the z and the y are the ones that are in the plane, and the x-axis is the one coming out at you. Well, this spiral, cosine t, sine t, t, if it's just cosine t and sine t, it is the circle, the unit circle in the xy plane. However, with this t, now we have this, so what you're going to get is it's going to be from 0 to 3 pi over 4, so we're going to move along 135 degrees, and we're actually going to end up coming up. So if I were to take the xy plane and look at it just from the xy plane, I would see this curve that's going up like this, sort of like a ramp of a parking lot that works in a spiral. That's exactly what it is. It's basically a spiral, because now you're not just moving along x and y, you're also moving along z for every step that you take. So you're going like this. So we're going to let's see what we can do with this line integral here. Okay, so f of c of t, so let's find f of c of t. That's going to equal, actually I don't need this because I'm not talking about a vector. We have cosine squared t times y, which is sine t, times z cubed, so times t cubed. So this equals, in general we put the variable first, so t cubed cosine squared t sine of t. Well, now let's go ahead and find c prime of t. Well, c prime of t is minus sine t cosine t and 1. Now let's go ahead and find the norm of c prime of t, the length, in other words, of the tangent vector at any given moment. That's going to equal this squared plus this squared plus this squared, all under the radical, so sine squared plus cosine squared plus 1 under the radical, and sine squared plus cosine squared is 1, 1 plus 1 is 2, so we have radical 2. So the integral of f along this particular contour is equal to the integral from 0 to 3 pi over 4 of t cubed cosine squared t sine t times radical 2 dt. And then when we put this into mathematical software, because again, I'm not going to do this by hand, we get the following answer. Minus 13 pi over 12 plus 9 over 28 pi cubed minus 41 over 27 plus 15 over 32 pi squared. So again, it's just a number expressed in terms of pi and other numbers, nothing simplified. Put it in a calculator, you're just going to get a number. So it is possible to actually have a function of several variables and integrate that function, just like it is possible what we've been doing, it's what we started off with, integrating a vector field over a certain path. So that's it. Everything is exactly the same, except the definition is slightly different. Instead of doing a dot product, you are just multiplying by the norm of the tangent vector instead of dotting it with the vector itself. So that's it for line integrals here. Thank you for joining us here at Educator.com, and we'll see you next time for a further discussion of potential functions. Bye-bye.